Okay, now we are in chapter 7. It's about eigenvalue and eigenvector. Okay, so for introduction, so we have A is a matrix and time n is a square matrix, and X is a vector in space n. Then usually there is no geometrical relationship between vector X and matrix. So we don't know what is the geometrical relationship, the shape or figures of this matrix combination or product of matrix and vectors. We have no idea, so that's why we need to find eigenvalue and respective eigenvector to show the direction or the magnitude of a combination or a product of matrix and vectors. Okay. Okay, for definition, if A is a matrix and scalar lambda is called the eigenvalue of matrix A. Lambda is a respective respective value, corresponding value for matrix A, or it is specifically called eigenvalue of A. If there is a non-zero vector x such that Ax equal to lambda x. Okay, A is a matrix multiplied by vector x, and it is equal, lambda is a scalar, means that it is only a single value, multiplied by a same vector x. So we want to find what is the corresponding scalar that represent matrix A. Okay, if lambda is the eigenvalue of A, then every non-zero vector x such that Ax equal to lambda x is called the eigenvector of A corresponding to lambda. So this is what we call eigenvalue. We want to find eigenvalue that represents a matrix A where Ax is a product of matrix and vector x, and it is equal, lambda is the corresponding scalar for matrix A, also multiplied by vector x. The solution for x, so once we obtain lambda, the scalar, we are able to find vector x. So the vector x itself is called eigenvector of A that correspond to scalar lambda. Okay, next is finding eigenvalue. Okay, let A be the matrix, square matrix n times n. So we can write Ax equal to lambda x as stated earlier as Ax equal to lambda times identity x. Okay, so that lambda times identity represents scalar lambda. So both A and lambda identity is a matrix. Or equally, we can bring lambda identity to the right side and factorize it. It becomes A minus lambda identity x. We bring lambda identity x to the left side. So we can factorize it so that it becomes A minus lambda identity x. And the right side becomes 0. Okay, so this is the matrix equation, the homogeneous matrix equation. So remember the properties of homogeneous matrix equation. For homogeneous system of equation to have a non-trivial solution, the determinant of matrix A minus lambda identity must be 0. So the determinant must be 0, then only we have the equation of system, the system of equation, the homogeneous system equation as having non-trivial solution. Meaning non-trivial solution, meaning that there is a solution which is not all value x 0. So using cofactor expression for determinant, remember to solve the determinant by using the cofactor expressions, again in the formula of determinant, we are able to get the equation as lambda plus C1 lambda power n minus 1 plus until Cn minus 1 lambda power 1 plus Cn. So this is the cofactor expression as we have learned earlier in the determinant topics. Okay, but it is put in the equation, and this is called characteristic equation of A. So solving this equation, we will get the eigenvalue of A. So this is in the notation form. So later we'll show by using example, so you can clearly have an idea how to get this characteristic equation by using numbers. Okay, so this is the one of the properties. If A is the upper lower triangular matrix with size and time n, then the eigenvalue of A is the diagonal entries in A. If A, the coefficient matrix given is a lower or upper triangular matrix, then the eigenvalue is just having the product of the diagonal entries in A. That will be the eigenvalue of A. Okay. One statement here regarding the coefficient matrix. If A is an upper or lower triangular matrix with size n, then the eigenvalue of A is the diagonal entries in A. So once we have A in the form of upper or lower triangular matrix, so the diagonal will represent the eigenvalue of A. Okay, for finding eigenvector, earlier we find eigenvalue. So the corresponding eigenvector will be the respective value of x. Okay, let's say once we obtain eigenvalue of A lambda, once we obtain the lambda, we replace the value of lambda in this equation, in the homogeneous equation here. A is the metric coefficient. Okay, now we obtain the lambda, replace equation lambda here by the one we obtain, and solve this one. And finally, we have another set of equation of x, x1, x2, x3 that represent vector x. So the vector x is the eigenvector. Okay, now we look at examples how to find eigenvalues of matrix 3 times 3. Okay, given an example of matrix 3 times 3 like this. Now find eigenvalues for matrix A. Okay, so first we need to form the characteristic polynomial of A by using this equation, determinant lambda identity minus A. So we form lambda identity minus A. We obtain this matrix. So we just put lambda identity, lambda time identity is 1 0 0 0 1 0 0 0 1. Okay, this is lambda time identity, and then minus matrix A. Matrix A is this one. Okay, minus matrix A this one, and then we obtain this matrix. Okay, lambda identities. So solve this equation, we have this matrix. And then find determinant of A, determinant of matrix, this matrix, determinant of lambda identity minus A. You are having this one. Okay. So now find the determinant using formula of determinant. Using formula of determinant, we have this equation. Okay, try do on your own, obtain determinant of this matrix and be able to find this equation. This is called characteristic polynomial equation. Okay, this is called characteristic polynomial equation. Okay, So once we have this, set this to 0. Okay, we set this equation to 0, this characteristic polynomial, set this to 0, and then solve the equation to find value of lambda. So from here, you can use your calculator. We obtain value of lambda is 4. Second lambda is 2, second solution for lambda is 2 plus third 3, and third solution for lambda is 2 minus third 3. Okay, example to find eigenvalue for A, for example for 2 times 2 matrix. Let's say A is 308 minus 1. So for lambda identity is lambda 0, 0 lambda. So the characteristic equation of A by solving this equation, lambda identity minus A is this one, this matrix. Find the determinant of this matrix, set to 0. So we have a characteristic polynomial equation as lambda square minus 2 lambda minus 3, 0. Solve this quadratic equation. We have got value for lambda or eigenvalue is 3 and minus 1. Okay, in order to find eigenvector, actually eigenvector we can have many eigenvector with only one eigenvalue. So therefore we need to find basis for eigenspace, then only we are able to find eigenvector. Okay. Okay, let X be x1, x2 is an eigenvector of A corresponding to lambda if and only if X is a non-trivial solution of lambda identity minus AX equal to 0. This one from the definition of eigenvector. Okay, from the definition of eigenvector, we have this statement. So by using this, we will need to find what is the eigenvector for this homogeneous system equation here. Okay, so using this equation, so we set this equation like this. So let lambda be the eigenvalue, the first eigenvalue that we obtained earlier. Okay, lambda is 3, lambda 3, put lambda 3 here. So we have this one, and from here we derive the equation. We have equation like this. First equation, since this is 0, we don't have first equation. We only have second equation, minus 8x1 plus 4x2 equals 0. So we have two variable with one equation. So we have extra variable. If we have extra variable, then we need to set one extra variable as another variable. So let x2 be t. Let x2 be t. So now the equation become minus 8x1 plus 4t equals 0. So therefore, x1 become t over 2. Okay, and x1 and x2 will be solution with other variable. So the solution for x1 and x2 become t over 2 and t. So we factorize t. So inside vector is 1 over 2 and 1. And the vector here, the value of vector here is the eigenvector. Eigenvector. Okay, it's an eigenvector. Actually, this is a basis for eigenspace because this is the basis for eigenspace. This is the also eigenvector. Eigenvector can be a multiplication of t. Okay, if t is 1, then the eigenvector become half and 1. If t is 2, then eigenvector become 1 and 2. If t is 3, then eigenvector become 3 over 2 and 3 and so on. So we have many eigenvector with eigenvalue 3. But basis for eigenvector is this one. This is the basis for eigenvector. So we call it half and 1 is a basis for the eigenspace. This is actually the right definition. This is the basis for the eigenspace corresponding to lambda equal 3. We can have many eigenvector with this basis with different value of t. Okay, for another eigenvalue which is -1 that we obtained earlier of matrix 2 times 2. So we again we substitute lambda equal to -1 in the corresponding equation. So we have this matrix equation. Solve this, then we have -4x1 equals 0. This is a trivial solution, meaning that we are not able to find what is the value for x1 because the only value for x1 is only 0. So therefore, there is no basis for eigenspace corresponding to lambda equal -1. Because we have only a trivial solution. Okay, next is diagonalization. Okay, a square matrix A is said to be diagonalization if there exists an inverse matrix P such that inverse P, AP, is a diagonal matrix and P is said to diagonalize A. Okay. So P inverse, so the key point here is using P inverse AP. It becomes a diagonal matrix and matrix P is said to diagonalize A. So meaning that any matrix P that we can find with operation P inverse AP, it makes a diagonal matrix. P is said to be diagonalize A. Okay, so the following theorem will be used to find P. Okay, so normally in this topic, we will ask you to find what is matrix P that diagonalize a given matrix A. So if A is an n and times n matrix, is square matrix, then A is diagonalizable if and only if A has a set of n linearly independent eigenvectors. So this is the theorem to be able for us to find matrix P that diagonalize a given matrix A. So a method for diagonalizing a matrix is using these steps. Okay. Step 1, find n linearly independent eigenvectors of A. So we will be asked to find an eigenvectors of A given a matrix A. Then we'll be asked to find eigenvectors of A. Okay, let's say P1, P2 until Pn is a set of eigenvectors for A. And then for matrix P, then we list down all the vectors we obtain, all the eigenvectors that we obtain in step 1. And let it be matrix P. And then step 3, matrix P inverse AP will be diagonalized and will have the eigenvalues corresponding to vector P1 until Pn respectively as its successive diagonal entries. Okay, this one just stated steps. You will understand more once I give you an example. Okay, in determining whether a square matrix A is diagonalizable or not, we are also determining whether there is a basis in space N consisted of eigenvectors of A. So this is a statement. So we will see in the example. Okay, example, find matrix P that diagonalize a given matrix A given by this matrix. So first, we need to find a characteristic equation from determinant lambda identity minus A set to 0. Okay, this is a characteristic polynomial equation. So from this one, okay, try solve this characteristic equation and you'll be able to get this equation. Okay, from the determinant of this one, get this equation. So from here, we get lambda equal 1 and lambda equal 2. Okay. And then for lambda equal 2, remember our earlier notes. From each lambda will give you a different eigenvector, corresponding eigenvector. Okay, for lambda equal to, we'll get these two eigenvector. So I want you to do this as exercise. From lambda equal to, you'll be able to get these two eigenvector. Okay, from eigenspace. Remember the notes, our notes earlier on finding a basis for eigenspace. Okay, from that we'll get two eigenvector. Okay, for lambda equal 1, we'll get this eigenvector. So therefore, a basis vector for matrix P is given by P1 for column 1, P2 column 2, P3 column 3. So this is a matrix that diagonalize A. So in order for us to confirm that P diagonalize A, we verify from equation or from operation P inverse AP. This is P inverse, so you need to find the inverse of this one first. P inverse A and P. Okay, so multiply all these three matrices and finally you will get a diagonal matrix which consists lambda 1, lambda 2 and lambda 3. So this is how you verify that will obtain matrix P diagonalized matrix A. So finally we'll get a diagonal matrix which consists lambda 1 eigenvalue, lambda 1, lambda 2 and lambda 3.